Good morning. Glad you're up and Adam and ready to join me in class today online. Today we're going to continue our discussion about when quantities are not equal, right? Instead of equations, we're looking at inequalities, things that one thing is larger than another or smaller. So solving inequalities and using inequalities. Let's take a look at our textbook. So our title today is How Can I Use Inequalities? And the subtitle is More Solving Inequalities. So yesterday we talked about how to solve inequalities, and I think the big idea that I want to reiterate is if you're presented with an inequality, treat it first of all like an equation, right? Replace the inequality symbol with an equal symbol and solve it to find what we find the boundary location. The boundary location is the point on a number line, particularly if we're looking at an inequality with one variable. It's the point on the number line that divides the number line into the region with solutions and without solutions. Once you have that boundary condition, that boundary location, then we just test on either side to see which side of the boundary is working. So let's look at a couple examples of that. Okay, I have about 6 of these problems for us to look at, and I encourage you to maybe do a quick pause and just see, can you do it, and then unpause and see if you have the same solution. So this first one, again, find the boundary point, and then once we have the boundary point, test and see which side's working. So if I was to solve this as an equation, of course, it's just x minus 7 is equal to negative 2. If I add 7 to both sides, we get that x is 5. So our boundary is at 5. So I'll go ahead and put, here's the number 0, here's the value 5. And I just test, and as I've said in class yesterday and online, my favorite test point is 0 if it's available. And I say if it's available, that just means if my boundary is not 0, I usually test 0. So if I plug the value 0 into the original inequality, this becomes, if x is 0, that says negative 7 is less than negative 2. Well, that's true, right? It's clearly true that negative 7 is less than negative 2. So that's the direction that we're going to go. Now, this particular inequality, it was strictly less than, so our boundary is going to be an open circle, and it's going to be everything that goes from there to the left and through the number 0. So this is our solution. Our solution are all values that are strictly less than 5. And once I have that, I can also write that down this way. X's are less than the number 5. All right. Another thing that you can do while you're working today, if you want to have a different view of things, is you can always take a look at things in Desmos. In Desmos, I did go in and I turned off the y-axis. I don't need to see that. And I also hid the grid. So this is what it looks like in this setting. And we're expecting here to see an open boundary at 5, meaning 5 is not included. And it should be everything to the left of that. You can see when I turn this on, yeah, it's indicating an open boundary at 5 by using a dotted line, dash line, meaning 5 itself is not a solution, but anything to the left of 5 is a solution. Let's go back and take a look at our next example. For our next one, we have 3m. 3m plus 2 is less than or equal to 8m minus 5. I think I'm going to go ahead and subtract 3m from both sides. So that's, again, I'm looking this as an equation. Plus 2 is equal to 8m minus 8. So if I subtract 3m from both sides, this becomes 2 is equal to 5m minus 8. If I add 8 to each side, this becomes 10, so 10 is equal to 5m. And dividing both sides by 5, we get that 2 is the location of our boundary. And yes, it's an m, but we're not going to worry about it. It's just a different variable. So if I look on a number line, here's the number 0, and my boundary is at 2. This time, because the symbol was less than or equal to, I'm going to have a filled in or solid boundary indicating that 2 itself is a solution, and then I need to test and see which side works. So Again, I'm going to plug 0 in. It's my favorite test point if it's available. And when I put 0 in for both the 3 times m and the 8 times m, this becomes 2 is less than or equal to negative 8. Well, 2 is not less than or equal to negative 8. So this side, the side with 0, does not contain solutions. The side that contains solutions is everything to the right of 2. So this is the direction that we go. And again, if we go back to our friend Desmos, whoops, and I'll just delete this one. And I have to use x, so I'll say 3x plus 2. And to do less than or equal to, then you just type less than and then follow it with an equal. And then 8m, 8x, I have to use x, and then minus 8. And when we do that, you can see that we do have a solid line at 2, solid line at blue, solid line at 2, indicating that 2 is where the boundary location is, and it's everything to the right of 2. Finding our boundary location, I turned it into an equality, and I'm going to apply fraction busters and multiply every single term by the number 3. Here's a term, here's a term, here's a term, and here's a term. So each of those are going to get multiplied by a 3 or get a new factor of 3. 2/3 times p is going to become 2p. This is 2 times p. Minus 6 is equal to negative 12. So that was just me multiplying everything by 3. Now, if I add 6 to both sides, we get that 2p is, I'm adding 6 to this side. That's going to make this side negative 6. And then finally divide by 2, I get p is negative 3. Okay, so on my number line, I have, here's 0, and over here is 1, 2. Here's my negative 3. So that's my boundary location. This was greater than, right? It's not greater than or less than, so it's going to be an open boundary. And then I just test 0. So if I plug 0 into that equation, it's going to become negative 2 is greater than negative 4, which is true. Negative 2 is larger than negative 4. So that means the side with the 0 contains the solution, so we are going this direction. And for a quick visual confirmation in Desmos, we do see that negative 3 is our boundary, it's an open boundary, and it's everything to the right of that boundary. Okay, on to D. I have set this up as an equality to find my boundary location. If I distribute, here I get 2 minus 3x plus 3 is equal to x minus 7. I'm going to add 3x to each side, and the 2 plus 3 is going to become 5. So this is 5. Let me not do 2 steps at once. 5 minus 3x is x minus 7. Adding 3 to both sides, we get that 5 is 4x minus 7. Adding 7 to each side. Adding 7 to each side, we get that 12 is 4x, and dividing by 4, we get that our boundary location is at 3. This is greater than or equal to, so we know that our boundary is going to be solid. Here's 0, and here's 1, 2, and 3. A solid boundary at 3, and then I test. My favorite test value is 0, so I'm going to make this x equals 0 and this x equals 0. When both of those become 0, right, when this is 0 and this is 0, this inequality collapses to 2 plus 3, which is 5, and 5 is greater than or equal to, 5 is greater than or equal to negative 7. And that is true. So our boundary is at 3, and it's going this direction. So our solution is x values are those things that are less than or equal to the number 3, right? And again, this was the statement that I got from my testing my boundary location. Because this was a true statement, I knew that this was the direction of the points, and then when I look at it, I can just say, oh, x's are less than or equal to 3. All of those values on that side will work. And again, because I'm concerned, because this is maybe slightly new to me, I do like to keep checking my work, and I'm checking in Desmos today. So in Desmos, I can see that I got exactly the same thing that I got when I did this on paper. My boundary was at 3, it's a solid boundary at 3, and x values that work are all of those things that are to the left of the boundary, so x's are less than or equal to positive 3. Okay, so for E, I have this inequality that I turned into an equation to find the boundary location. And a couple observations I see here. On the right-hand side, I do have a 2k and a 7k. Added together, that's 9k. And that's exactly what I have on the left-hand side. So I'm going to subtract 9k from both sides. When I do that, what remains over on the left-hand side is a negative 4 and 1. And on the right-hand side, I have a negative 3. Well, it turns out when I combine negative 4 and 1, I do get negative 3. And on the other side, I also get negative 3. So to me, that's a statement that is always true. And therefore, I believe that any value of k would be a solution to this inequality. And if I looked at this in Desmos, my expectation would be that there would be no boundary point, but that everything would work. So I'm going to say all values are solutions. And let's take a look at that real quick in Desmos. Well, interestingly enough, I'm going to stick with what I claim, that all values are solutions. But when I looked at it in Desmos, it's showing me nothing, and I was disappointed. I was thinking I would just see, I was thinking I'd see green in all directions, but I did not. But I do think that an important idea here is that in this particular problem, I can see that the left-hand side is less than or equal to the right-hand side. So because it says or equals, I think any value of k is going to make the left and right-hand side the same, right? Any value of k is going to make the statement negative 3 is negative 3. So it'll always be true that, if I wrote this out, that negative 3 is less than or equal to negative 3. Now, if this was not or equals to, if this was just less than, I think it would be a different story. And in fact, it looks like someone's trying to make that point in part F, because in part F, I can see that the left and right hand side are exactly identical. If I subtract 3y from both sides, I get this statement, 1 is less than 1. Well, that statement is always false, right? Regardless of what I select for y, it's always going to be false that a number is less than itself. It's possible for a number to be less than or equal to itself, but not less than itself. So on this one, I would say that there's no solution. All right, so let's finish the day then. The last thing that I want you to do is 2 problems, question 15 and 16. And it's one of those things where I highly encourage you to do these with people that you are comfortable with working with. So however you communicate with each other, and someone create a doc, share that doc. I would call it, section 9.1.2, and do question 15 and question 16. So we'll at least read through this and get started. So later on this chapter, we're going to do something regarding the United Nations, right? But for now, the UN needs your help preparing for future large-scale disaster. You'll need to help to find a solution not only that works best for the country you represent, but also accommodates the needs of each of the other member countries. To prepare for this task, the next several lessons will present daily problems to familiarize you with important issues concerning other countries. So write and solve an equation that represents the problem below. Okay, it says write and solve an equation. It doesn't say inequality. An equation that represents the problem below. There are a total of 193 member states, countries in the United Nations as of 2016. So it's like now it's 7 years ago. The member states are divided into regional groups, and then it starts describing these things. The Asia group has one less member than the African group. So if you hear what just happened, they described the size of the Asia group in terms of the size of the Africa group. So the Asia group has one less member than the Africa group. Okay. The European groups are smaller. Eastern Europe has four less than half the Africa group. So what's happening here is if we define a variable, we're going to use that variable. And remember that these have to add up to 193. And the question here is how many countries are in each of the 5 groups? So there are 5 groups. And I will be online all day if you have questions or you have a difficult time getting started with this. But my expectation is that you will define a variable, and I will just say because the Asia group is given in terms of the size of the Africa group, I would suggest let A equal the size of the Africa group and then go from there and see what happens. But remember, they do add up to 193 member states, and let's see how far you go. The other problem that we're doing is problem 16, and we'll look at this as well. In 1912, Japan gave the United States several thousand flowering cherry trees as a symbol of friendship. Similarly, the nation of Cameroon plans to give flowering sada trees to other countries this year. When asked to decide which sada trees make good gifts, Cameroon's chief arborist explained, "We plant sada trees when they are 6 centimeters tall, and they grow 9 centimeters every year. The trees only flower when they are taller than 150 centimeters." Okay, something to keep coming back to and reading. And perhaps there's an inequality in there as well. It's very important that the trees Cameroon gives flower this year, so they want them to flower this year. It would be considered an insult to receive a tree that did not bloom. Luckily, Cameroon has many groves of sada trees from which to select its gifts. How old must the trees be so that they will flower within the year? There's some discussion questions here. Discuss with your team whether an inequality or an equation is appropriate. Share your reasoning. Write and solve a mathematical sentence to determine how old the trees can be so that they flower this year. And then C, later the arborist added, "I almost forgot to tell you, when trees become very old, they stop flowering. Make sure you choose trees that are no more than 240 centimeters tall. Discuss with your team how you can use this additional information to make sure you choose trees will flower." Okay, so again, two class items, question 16 and 17. Those will occupy the rest of our classroom time together because we're at 20 minutes, so you have another 25, 30 minutes to complete 15 and 16. And if you have questions about either one of these, please join me online, and I'm here and prepared to help you. This is Mr. Roberts. Have a great day, and I look forward to seeing you again tomorrow.